Okay, so we'll talk today about the current mirrors and why do we need them. So first, let's remember when we are using a common source, we opted to use a current source as a load in order to have a larger output impedance, and that will allow us to get larger gains. So M1 here is the amplifying device, and M2 is the current source, or the amplifying device as NMOS, and the PMOS, and here with the VB. So M2 here, and this is M1. So M1 is the amplifying device, and M2 is the current source. And there is V out. We also, if you remember, used in the source follower as well. So this is VN, and another current source here with the VB. This is V out. Let's see, M1, and this M2. Here M2, we have here the M2 and the M2, those are all current sources. So we can see that the current sources, they are everywhere. We use them in multiple locations in the circuit, and they are useful for us. Now, since we can make them through these NMOS or PMOS devices with a certain biasing voltage, it's all good, everything is fine. What's the problem here? Why? What can be the issue? The issue is basically in generating this VB here. Generating VB can be problematic. How to write problem. Why is that? Because what we want is that we want to have a fixed VB that does not get changed with different variations, in order to get a fixed current source with a certain value that we are setting our circuit to operate in. So basically, we need to make sure that first, this current source, the transistor, is also should be operating definitely in the saturation region. So the VB. Now, let's assume that this VB is basically coming from a battery. And we have here ID. If you remember, since it's in the saturation region, ID equals half mu1 COX W over L of VB minus V threshold square. Okay, now the thing is that if the temperature varies like some certain degrees, for example, if you are in a very cold area, you are inside the house, and then you leave the house, the temperature will vary with the tens of degrees, and this will change. So we have V threshold and vary with temperature, even if we assume that VB quite fixed. However, even this is not a very good assumption, because the battery devices that they depend on operated by batteries, such as the cell phone, in the beginning, I mean, when the battery is full, you have a certain voltage, let's say 3 volt, But when the time passes and the battery start to discharge, then this voltage drops significantly. I mean, it may reach up till 2.7 out from the 3. So that is a thing about it. Even if the battery is good enough to generate this VB, this means that for each of those current sources in our chip, we need a very good battery for each one of them. This can be an issue. I mean, we don't want to have a tens of batteries for each small device that we are having. Imagine like for your cell phone, you will have 100 battery for all the circuits which they are inside it. That's not an ideal, or that's not acceptable solution. So we need to do something about it. Okay, so the issue is that how we should generate VB. I mean, we need a good VB that should be stable and allow us to get exact current that we are aiming for. One way is, for example, if you use a resistive divider. So for example, if I have here VDD and we have here R1 and down R2, and from here I'm applying at the gate of the transistor I out. Okay, so ID here again, half mu1 COX W over L. Now the voltage divider, or the VB here, will be R2 over R1 plus R2 times VDD minus V threshold square. And again, this VDD may change with time. I mean, it can also, because it's also coming from a battery that might discharge. So this is also not a good solution. So what should we do? Okay, let's have another page. Number one that we have is that battery, or it means that they depend on the value of the supply voltage or the voltage, because also supply voltage is coming from a battery. So they will be depend, and this battery might change over time. So the things, I mean, the current is not going to be fixed. So the first issue is that they are supply dependent. Now, there is another issue that can happen basically, is that number two is that they are temperature dependent, which they are the mu1 and the threshold voltage, or so they are basically change with the temperature. So the mobility and the threshold voltage of the device, they change with the temperature. So we need something that is basically independent of these changes, and that can be the ideal solutions. So let's see how can we reach over there. Now let's assume that we have one golden current source. Means that it's temperature independent and also supply independent. Okay, now from where this golden current source is going to come, there are certain types of the circuits that they are resilient to these changes. We call them the band gap circuits. So we will create it through band gap, and that's beyond the scope of this course. So I mean, this is an advanced circuit that we will, if in future courses, if you are interested, you can study them. But let's assume that we have this ideal current source that is independent of the changes in the supply and the temperature variations. So if we can somehow take this current source and parts in the circuit, this is going to be the ideal solution. But we want something to do that. So then copy this current source to multiple locations or multiple parts of the circuits that we have. But we want how we should do that. So assume that we have, this is our golden current source, let's call it IRF, that we generated from band gap circuit. Okay, and then we want something here. We have a black box that will basically create copies of this current. We have multiple copies here, I1, I2, and etc. Whether of the same value means I1 should be equal to IRF, or they are multiples of it. So how we should do that? How can we create these currents are in the down direction, some. Now, since these the current sources, how should I, like, what should I do with them in order to set their currents to equal multiples of IRF? How can I control it? Do I have control over what? I can control only the gate side of them. Since the source are grounded, I can control the gates. But how should I control the gate? By applying a voltage or by applying a current? Now remember that no current goes inside the gate of the transistors. Therefore, I am left with the only option of controlling the voltage that is being applied on this gates of these current sources that they are coming here. One way is that if I think of something what can be here, the magical part that is here to control these sources. So if I try to do this, so this is the same gate location, and if I have said we want to control the volts, so this is R1, and I have the IRF coming here. So VDD, IRF, and this is I1 here. Okay, so I am setting a certain voltage on the VGS of this transistor. So the VGS here will equal to the voltage drop, make a KVL here. In this loop, we'll see that the VGS of this transistor equal to IRF times R1. So ID will equals half mu1 COX W over L times F multiplied with R1 minus V threshold square. Now remember, in all of these, we are basically neglecting, in all cases, neglecting lambda. Can't write down here. Or assume lambda equals 0. Okay. Now, did I solve my issue? Did I get a clean, perfect copies of my reference current, or I still have an issue? What about this solution? Is it good or not? Unfortunately, it's not good because still mu1 is temperature dependent, R1 is also temperature dependent, and threshold voltage dose depend problem. And this is not a good solution. So we need to think of something different that can solve this issue. Okay. Any question till now? Okay, now let's make the first one. If you remember the diode connected device, okay, so it's a two-terminal device. The gate and the drain, they are shorted with each other, so it's like a single terminal. And if we want to study the IV characteristics of this device, so by applying a certain voltage here, V1, and measuring the output current I1 through this device. So let's try to plot this. So obviously, why we are interested in this device, because it's also always in saturation if it is on. Why? Why it is always on saturation if it is on? Because the VGS equals to VDS. Therefore, since VD and VG are shorted, VGS equals to VDS. And therefore, always VDS will be greater than VGS minus V threshold. This is always going to be correct. Therefore, this diode connected device is always in saturation if it is on, means if it has a voltage applied to it that is greater than its threshold voltage. So this means that this is V and this is I1. So until we are V1 equals to the threshold voltage of the device, if it is below the threshold voltage, the device will not be on and there is not going to be no current. Once the V1 reached to saturation, therefore it will follow the saturation equation, V1 minus V threshold square, and we will have like a square relation with the current. Okay, now what about how if we apply a current in this diode connected? Or let's say from this equation, how V1 is, what is the relation of V1 as a function of the current? So we can rearrange this equation and we can get that V1 equals to, taking the square root and dividing, will be V threshold plus square root of 2I1 divided by mu1 COX W over L. So if we want, if that was like on another time, if this was here V voltage, then the relation will look something like that. If the current is zero, means that, and otherwise it will become a square root relation. I mean, you don't need to worry too much about how the drawing is happening. Just this is for your visualization. Now, if this what I is the conclusion from this, if it means injecting a current in a diode connected device allows it, or well, it's not the right thing. Why it stopped? I think it generates a voltage. Means in this diode connected device, if I, instead of driving it with a voltage, I drive it with the current, something like this. And here I apply a current and measure, then it will generate a voltage, this V1 across its terminals. Okay, this is the meaning. So this is something, I mean, why we are talking about this diode connected transistor. This means it can be, let's try to have it and use it in order to generate this magical VGS for our circuit. So if we can do something like this, so this is we come back to our diode connected transistor with here a magical current or I1, and these they are shorted with each other. So now the voltage that is being coming at the gate of this M1 will equal to the same VGS of this one. Again, this is a VGS here, and this is another M2. So VGS of M1 will equal to VGS of M2 if we make this minus VGS2 plus VGS1 equal to 0, and therefore we have this relation here. So now let's see how the currents, they are related to each other. So I out equals, again, since it will ideally be in saturated of M1 equals V, VG, also we called it V1, the same, this is VGS or V1 minus V threshold square. Okay, now let's replace this V1 from we want to replace it with this one here. Okay, so now half mu1 COX W over L transistor 1. Now let's replace V1 with that relation. So it will be V threshold plus square root of 2 I1 divided by mu n COX W over L of M2, and sorry, minus V threshold. Okay, so now we can, and this is all square. So now we can cancel things with each other. So V threshold will go to the, because the two devices has the same threshold value. and the square root will cancel with the square. So mu and COX will also go with the mu and COX, and the 2 will go with the half. So what we are left with? We are left with I out equals W over L of transistor 2 times I1. And this is something that is so nice that we got it. Why? You can see now there is no threshold dependent. There is no temperature dependency because the sizes of the transistor, they are not depending on the temperature and they are not depending on the supply voltage. So we got a very nice relation that we can basically get a ratio of the currents that depends on the dimension of the transistors. And in this here, we will always select I out over I1 will become W1 over W2. So we will change the width of the transistors in order to get the currents that we are aiming for. And that's something is quite nice for us. So our circuit, if we just change how the drawing, just to flip this M2. So we will have, looks like this. This is I out, and here the diode connected device. Sorry, this is on IREF. This is M2 and this is M1. It's the same circuit. I just flipped the drawing of M2. Okay, so now here, I mean, if I change, if M2, let's say 1 micro and M1 is 10 micro, then I out will be 10 times larger than the value of IREF. Is there any question on this one? No questions. Okay, so now let's just do something. Okay. So we talked about the concept of this. So all this part is what we call it a current mirror. You cannot see my screen. Let me share. Okay, so this is a concept is called a current mirror. So it allows us to have multiple copies of the same or multiple values of a golden current source into multiple location of our circuits with a very simple scaling of the width of the transistors. So again, so the golden part is using this diode connected transistor in order to generate a fixed value of the VGS that will be basically, so the same VGS here of this MREF is equal to the VGS of M1. If you do a KVL here, you will find that their VGSs, they are the same. And that allows the currents to be the same if the widths are the same. If the width is increasing, then with the same ratio, the current is going to be increased. Just you need to make sure that you don't forget the connection of X value. So now let's look at this example, and find out how much current is going to have in I1 and I2. So you can see here that I have a fixed or a golden current source, the reference of 0.3 milliamp, and I want to copy it into I1 and I2, however, with the different values. So the L's, they are going to be the same. So I1 over I out is basically going to equal to what? The W2W, which is the width of this one, divided by the reference transistor. So it will be 2 over 3 because W is same as W, and therefore I1 equals 2 over 3 multiplied with the IREF here, with IREF, which is 0.3 milliamps. So this is going to be 0.1, so it will be 0.2 milliamp, and I2 will be 5 over 3 times 0.3 milliamp, the same ratio of the width. So this is going to be 0.5 milliamps. Any question? I mean, wherever you are copying it at any point, it will be the same based on the ratio of the transistors width. Okay, so you can see like just this is an example how many times we are copying the same reference current into our circuit. And that is something that's useful for us. So any question on this? Okay, I have a question for you. Let me just oh no. Yes.
Ma'am, could you please explain?
What?
Ma'am, the last example you did.
1 minute.
Yes, ma'am.
Let me share it again. This one, 1 minute. This one?
Yes.
Or the with the numbers one?
Ma'am, the previous one.
The previous. Okay. This one?
Yes, ma'am. Yes.
Yes. Okay. So basically, the general relation is that your I out over I ref equals to W, let's say, of the output transistor divided by W of the reference transistor. W here, the width of the transistor. Okay?
Yes, ma'am.
F equal the width of transistor M1 divided by the width of transistor reference transistor. So here the width is 2W and here it's 3W. Therefore,
Okay,
it will
yes,
be
I got it,
2W over 3W. And so it will be the same. You need to make the ratios every time.
Okay. And ma'am, also,
Yes.
how is M1, M12 and MREF connected?
How M1, yeah, here.
To the gate of
Basically,
M1.
here, I mean, there is another connection here. So the wire going to a gate of M1 and also continuing and going to the gate of M2.
Oh, okay. Thank you, ma'am.
Yeah, so the wire is connected. Welcome. Let's
Thank you,
see,
ma'am.
I have an welcome. Let me share something with you. Okay. So now assume, it's my right. I have a current I want that is basically going into ground, and I want a current to be copied here. Just so I need something in middle here. I mean, this is part of it in the box. How should we generate? Just let me. Yeah, so think little bit, and this is I out. I mean, in the previous case, our ref was coming and going into an NMOS device that's going down from a VDD. Here, in this example or in this question that I'm asking you, the VREF or the IREF, sorry, is going into the ground. So how should I copy it into I out? Can you think about it for 1 minute? You have 1 minute to think about it. So what should we do? The solution or the idea is that basically we are not only limited by current source or by current mirrors that they are formed through NMOS devices. We can also form current mirrors using PMOS devices. So if we do something like this, we have here a diode connected PMOS VDD. Sorry, not here. The gate and the drain, they are shorted with each other. So here I have another PMOS device. All they are sharing the same VDD. Therefore, my current, this is IREF, and ref, this is M1. I mean, based on the ratio of M1 and MREF, I1 will be multiples of IREF. So we form this current mirror. So again, we have a diode connected transistor, the same VGS of MREF and VGS of M1, they are the same. So now we have an excellent copy of I1 that we can assume it as another golden current source here, and we can basically replicate it to this NMOS device. This is M2 and M3. Okay. Again, so I have that current that is going down into the ground. How can I copy it from IREF into I out? What circuit in the middle I need to make this copy? So the idea is that I use first a PMOS current mirror. This is the first current mirror. And then the output golden current mirror, I then mirror it into I out with an NMOS current mirror. So this is an NMOS current mirror, and here this is a PMOS current. Is this clear? So just let me give example with the numbers. Assume that IREF is 100 microamp and MREF, they all, Jamshed is asking, could I repeat what current mirrors are? Current mirrors, I mean, in general, their definition is that they are the configuration of the circuit that allows you to make a copies of your current into a different part of your circuits. So this is the general definition now. In reality, in the part of like how they are formed in a circuit, in this what I am showing you in the circles, the green circle with the IREF is basically the input, is the PMOS current mirror, and so it allows you to copy IREF into I1, and the NMOS current mirror allows you to copy I1 into I out. Okay, is that clear? Jamshed, did you get it or not yet? Yes, okay, good. Okay, so current mirror allows us to copy the current. So we, from the diode connected side current into the other normal or the current source. So we copy from MREF, we copy IREF into I1 and from I1 into I out. Now I just wanted to give you examples with the numbers, and this question like looks nice for the exam or for a quiz to be able to identify what values of a current you will get. So let's just now randomly give numbers. So if IREF equals to 100 microamps and M1, all L1 equals to LREF equals to L2 equal to L3. All the L's, they are the same. So we will just depend on the ratio of the widths. So ref, sorry, W. This is assume it's 1 micrometer, and W1 equals to 2 micrometer, W3 equals to sorry, W2, this one, and W3 equals, let's make it 8 micrometer, just randomly, any numbers. The main idea is to get the point. So the question is asking what is the value of I out? Okay, so what should we do now? We need to find first what is I1 and then what is going to be I out. So IREF or I1 over IREF equals to W1 over WREF, and therefore W1, which is 2 micrometer divided by WREF, 1 micrometers times the 100 microamps. So micrometer go with the micro, it will be 200 microamps on this. Is in relation with the IREF, and the same I1 is going into M2, so it is acting as a new reference current for the NMOS current mirror that we have here. So we will have I out over I1 equals to W3 over W2. Okay, this, I hope you can see what I'm writing. So it will be from here that I out equals W3 is 8 micrometer divided by 4 micrometer times the I1, which is 200 microamp, and therefore it will be 400 microamps. Is this clear? Any question on this? So first you need, regarding this current mirror, what do you need to know? You need to find how you can find the currents at any particular location in the circuit. And also if I ask you to draw from this certain point, from I ref side here till I out, how you can find this current mirror, form the current mirror with this value, I mean, then you need to be able to design it as well. Okay, any question on this, or we're done from the topic of current mirror? We can move to other topic if no other question. Seems to be no question. Okay, let me just save this. Okay, so now we are basically going to talk about the differential signals. And here we are starting on chapter 10, which is about differential amplifiers. But before going into the differential amplifiers, we need to talk about the differential signals. I am not sure if you have ever used them previously or not, but it's good to talk about them, how they are coming from, and why do we need them, and all that. Okay, let's basically, we have to look at an example of electrocardiogram, which is the ECG hospital to study the behavior of the heart function, and if so the ECG waveform, if the cardiologist look at it, they can identify if there are any problems of the heart of the patient. And how do usually they measure it? So if we have the patient here, excuse my drawings. So basically they fix, let's say, an electrode on the arm of the patient and one electrode on the ankle of the patient. And this is, they connected to ground, while the one that is coming here, and let's say around 10 times the ECG waveform, it looks something like this. Each of these peaks belongs to a heartbeat. That so the amplitude of each one of them and duration and time, it tells something to the cardiologist that about the functionality of the heart when each chamber of the heart operates. So each of these wave is linked to that the cardiologist can understand it. And the amplitude basically here can go maximum to few millivolts. So that's why it's a very small signal that can be sensitive to noise. So we shared the ground of the amplifier, and then you have an analog to digital, where we digitize the signal through ADC. And then we have some digital signal processing in order to extract more information from the signal. Okay, but at this moment, we're concerned here in the initial part of amplifying the signal. So basically, when you put the patient to measure their signal, they are in a room and you have electrical wires everywhere. So this connection here can basically pick the signal from these wires, and they can couple, and you will have noises that coming into this line. One example of this noise is the 50 hertz, or in the US, other parts of the world, it's sometimes 60 hertz, sometimes 50 hertz noise signal that can couple to your signal. So you will basically have the 50 hertz wave that you, those small heartbeats that they are coming every heartbeat. So your signal will be quite corrupted. The 50 hertz will be very larger amplitude compared to the amplitude of the ECG signal. So our desired signal is unfortunately going to be highly corrupted. So one other way to solve this issue is that you basically connect another hand, another arm of the patient with another electrode, and have some amplifier that is going to amplify the difference between those two signals. I mean, and then, so if both sides are prone to the same noise that is coming from the lines, the output, I mean, this, so if we have equal noise on this, let's call this V1, and this is V2. So the difference between, we are amplifying the difference between V1 and V2. So we are going to subtract this noise. This noise will going to be removed. Is this clear until now? Any question? So if only one input is coming, if it has a noise, there is no way that I can get rid from this noise. But if there are two lines that they are having a signal and having the same noise, when you subtract them, the noise will cancel with each other, and then you will get rid from the noise. And that's something good. We don't want the noise, we only want the signal. So here will be amplifying is V1 minus V2 will be amplified with a certain gain AV of this amplifier. Let me add with another. Now, given that V1 is not equal to V2 because each one of them is coming from a different arm, then we will have more clean signal as compared to the signal if only one electrode is coming and forming our desired signal. Okay, so now this gives us to define the differential signals. So let me just save this. If we want to define the differential signals, they are two signals. And there are on those two signals for them to become differential signals. Not any two signals in the world can be a differential signal. There are conditions on them. The first is that they vary the same amount and in opposite directions, let's say, on opposite values. I will explain this. Means that if this is V1, V2 will look something like this. So this is V2. So they are from this midline here, the same, I mean, up and down, they are of the same height, difference from this midline. And basically, they are in, so when V1 goes up, V2 goes down. And when V2 goes up, V1 goes down. So they vary with the same amount, but in opposite directions. Okay, so they are 180 degree out of phase from each other. Okay, now the second condition, they have the same average or DC value, what we call it. Means this average value, let's call it this average value has a name or common mode voltage, which is I just showed you here in the green. So this is called VCM. So they are moving up and down with the same amplitudes around this common mode voltage or the DC voltage in the middle of them. Okay, there can be, for example, they achieve the first condition, but they do not fulfill the second one. For example, if you have these two signals, so the one is going up and the other is going down, when the other and they have similar amplitudes up and down, the same values here, average, and therefore these are not differential because their DC, they don't fulfill condition 2. This is not a differential signal. Okay, is there any question on this? Okay, now let's continue. If just I want to identify the different, I mean more, if we can represent these equation or these signals with the sine waves. So V1 of t will be equals V0 sine omega t plus VCM. So it's a sine wave with this maximum amplitude here is a V0. And basically the other one, what I wanted to say, the frequency of it is omega, and it's around a DC value of VCM. V2 of t will be minus V0 sine, because it's in the opposite direction, plus VCM. Now, if we talk about V1 minus V2 will equals to 2 V0 sine of omega t. So we get to both of them. Okay, so if we just want to see that the peak amplitude of V1, V2, and V1 minus V2. So So V1 will have a maximum amplitude of V0. V2 will also have a maximum amplitude of V0, and V1 minus V2 will have a maximum amplitude of 2V0. So you can see that I have more wider range when I use a differential signal compared to those type of signals that basically they are, we call them single-ended signals. Okay, so each one of those V1 and V2, they are called single-ended signals, while V1 minus V2 is a differential signal. Basically, it's the difference. So the single-ended signal, they are with respect to zero, or to ground, sorry. While a differential signal depends on the difference between the two single-ended signals. It's not with respect to zero. Okay. Any question on this? Okay, so now how can we generate these differential signals? So for example, if you have a microphone, and then there is some output signal that is coming from it, which is just a single-ended signal. How can you transfer it into a two differential signals? One way, but it's not limited to it, if you use a transformer in this way, there's some coupling in the middle, you can convert this input signal into the single-ended into differential signals. I mean, there are multiple other ways. Okay, now if there is any noise that comes into this, at this side of the signal, then your all output is going to be corrupted. While if it comes on the differential part, it's going to be canceled, because your signal is just ultimately the difference between those two signals. And if there is a common noise to both of them, then it will be canceled out. While if anything comes on this before converting the signal into differential, then we will there is nothing that we can do. We have lost our signal. Okay, so now we can see that there is basically an advantage of using differential signals. And basically there is one very useful type of circuits to amplify these differential signal, which we call it the differential pair. Basically, it looks something like this. So this is VDD, it's RD, and here RD. Here we have V1 and V2, and we have another V out 1, and here V out 2. So we have this differential V1 and V2. It has two outputs, V out 1 and V out 2. So the two differential input signals, they can be applied at V1 and V2. And we have two identical resistors, RD as the loads, and we have a current source here, and a tail current that we call it ISS. So typically we have our differential amplifier to be identical across this midline between them. So they have to be symmetric across this line. And it's this is among the most used circuit components or topologies. In many, I mean, every circuit will have almost this differential amplifier. So it's widely used, has many applications, and we will discuss its operation and how to derive the gain for it, and all the details of it, the large and the small signal analysis of it in the, regarding what we have talked about it today. You can ask any question. Okay, then we can stop here and we'll meet next Monday, inshallah. We have a quiz next Monday, and you have also an assignment to do. Can I explain this figure? Okay, so basically, again, this is the figure of the differential amplifier. We are still did not discuss the details of it, how it works. We just, I am telling that the inputs, the differential signal that we have discussed, the definition of the differential signal, they will be applied at the input terminals V1 and V2 of this amplifier, and we will have some amplification at V out 1 and V out 2. We'll discuss them in details. So if you look at half of the circuit, you can assume that it's basically you can see two current common source amplifiers. They are connected with their source side down and with an ideal at this moment current source down. So that is just the initial introduction of it. The exact operation I did not explain. That we will do in the next class, inshallah. Okay, I just did not want to tell you that we have a differential signal and you don't know at all what is a differential signal. So we needed to do some bit of introduction for it. I hope that was clear. Any other question? From this amplifier, we will amplify the difference between those two input signals. So like when I just discussed where it went. Here, so inside, is it 1 minute? Inside this amplifier, you can see that I'm taking two input signals, V1 and V2. They will, inside this amplifier, we will have a differential amplifier that is going to amplify the difference between those. It's a single line, but I mean, we can have two lines, each one V out 1 and V out 2. We'll discuss that in detail, but the main thing is that you need to know that the differential amplifier amplifies the difference between the two input signals, V1 and V2. Okay. AV is here again. Okay, somebody else is asking question. 1 second, let me see, read it. For a current mirror, is it important that the two transistors used are of the same type, 2 NMOS or 2 PMOS? In the same current mirror, yes. I mean, you cannot, where those went? Means I cannot here have an NMOS, sorry, here a PMOS and I connect an NMOS here, because you know the mobility of the NMOS is different from the mobility of the PMOS. So currents, and the connection might not even work. So yes, in the same current mirror, you have to have the same either NMOS or PMOS. And if you want to shift from NMOS to PMOS, as we did in this example, so this is a very good example to show you how you can have it like a transfer from NMOS to PMOS or vice versa. So I think if you try to exercise in yourself how we can move from here this is an eye out and here IREF. How can I move from IREF to I out? IREF and this I out is coming onto a PMOS. Try to do the circuit yourself. Are not able to do it, then let me know. I think this is a very good example that will allow your mind to see if you are know how to link the things together. So this design the current mirror or mirrors, maybe here not single one, to have this IRF is let's say 100 microamp, and I out I wanted 600 microamp. Connect PMOS to IRF and connect the gate of PMOS to the gate of the other. This IRF cannot be connected to a PMOS. This IRF has, because it's providing current, so you need a device to sync the current. And the NMOS is the only one who sync current. PMOS, they give you like a sourcing the current direction. You need to be careful in it. Okay, I can see how we should do it. It's somehow opposite of what we did previously, but please think about it. Try to show me your design either through email or next time. If you want to, you can give you 5 minutes to discuss your design. So that's most. Okay, any other question? Okay, this means we can stop here and have a great long weekend. Allah Hafiz.